Today we will be doing the second session of the chapter Permanent Magnets. We all know that the Earth has its own magnetic field. Now, this is the geographical axis of the Earth, the geographic north and the geographic south. And this is the magnetic axis of the Earth, the magnetic north and the magnetic south. You will notice that I have put a dipole right at the center of the Earth. So this dipole represents the magnetic field due to the Earth. The dipole moment of this magnet is 8 into 10 to the power 22 joules per Tesla. Now, you will notice that there is an angle between the magnetic axis and the geographic axis. In fact, the angle is 11.5 degrees. So, if you consider a point P anywhere on the Earth's surface, and if you draw a plane which connects the point P with geographic north and geographic south, then this plane is called geographical meridian. And if you draw a plane which joins the point P with magnetic north and magnetic south, so this plane is called the magnetic meridian. Now you will notice that there is an angle between the two planes. This angle theta is the angle between the magnetic meridian and the geographic meridian. So theta is called the declination. Theta is known as the declination. Also, the resultant magnetic field is represented by B. The vertical component is BV and horizontal component is BH. And the relation between them, BH is equal to B cos delta, where delta is called the angle of dip. So these are the various parameters. The plane joining the point P with geographic meridian, geographic north and geographic south is called geographical meridian. The plane joining the point P with magnetic north and magnetic south is magnetic meridian. On the magnetic meridian, B is the field. Its components are BH and BV. BH is equal to B cos delta. So this is the relation. Delta is called the dip at that particular place. Basically, you know that if this is a bar magnet and this is north and this is east, so you know that for this bar magnet, the resultant field at a point, suppose like this, the resultant field will point in this direction, and if it is, suppose over here, this is end on, this is broadside on. Suppose if it is over here, the resultant field will point in this direction. So if you have a bar magnet, there will be a location which is broadside with respect to the bar magnet, where the Earth's field and field due to the magnet will cancel each other. So this is the field due to the magnet, this is the Earth's field, they'll cancel each other. See, there will be a similar point on this side where the Earth's field and the field due to the magnet will cancel each other. So these 2 points, they are known as neutral points. So neutral points are those points where the resultant field due to the Earth and due to a particular magnetic material like bar magnet will cancel each other. So for a bar magnet with north pole pointing north, these 2 points will be the neutral points. Suppose you have a bar magnet with south pole pointing north. So you know that this will be the Earth's field and this will be the field due to the magnet. So this is a neutral point. And similarly here, this is the neutral point. So these are the 2 neutral points. So a neutral point is a point where the field due to the Earth and the field due to the magnet, they both cancel each other. Now, in this particular session, we will be focusing on 2 instruments. One is galvanometer and the other is magnetometer. So we will be focusing on these 2 instruments. Galvanometer detects the flow of current and magnetometer helps us to find the magnetic moment of a permanent magnet. So first let us discuss galvanometer. Galvanometer is of 2 types. The first one is called a tangent galvanometer. Now in a tangent galvanometer, there is a circular coil like this, and right at the center there is a compass needle pivoted at the center of the coil, and this entire assembly is held on a frame. Now, if you allow current to flow through this coil, so when current flows through this coil, let us say that the coil has n turns, so you know that the field at the center of this coil is mu naught Ni by 2R. Suppose this coil has n turns, the field at the center will be mu naught Ni by 2R. Now, when the experiment was started, right at the beginning, it was ensured that the plane of this coil is set along magnetic meridian. So right at the beginning, it was ensured that the plane of this coil is set along the magnetic meridian, and this is the field at the center. Now suppose if this is the direction of current, then the field will be into the board. So that means, suppose if I represent this field as B, then you know that BH will be along the magnetic meridian. BH is the horizontal component of Earth's field. You know that BH will be along the magnetic meridian, and this B will be perpendicular to the plane. So that means B and BH will be perpendicular, and the resultant of B and BH will be represented by this diagram. So B is mu naught Ni by 2R, and BH is the Earth's field. The resultant of B and BH will be Br. What is the significance of the direction of BH? This compass needle, it will finally come to rest along the direction of Br. So the compass needle will come to rest along the direction of Br. So M into Br, these are the two forces on the north and the south of the compass needle. As you can see, these two forces are cancelling each other. That is why the compass needle is steady in that position. Now if you look at this diagram, it's pretty clear that tan theta is equal to B divided by BH. So that means B is equal to BH tan theta is equal to mu naught Ni by 2R So I is coming 2R into BH into tan theta by mu naught N. As you can see, all the terms inside this bracket, 2 into R into BH by mu naught N, all of them are constant, and you can write all of them together as K. So that means I will be equal to K tan theta. So if I is equal to K tan theta, then di will be K sec square theta d theta. So di by I, that means you have to divide these two. Will be 2 d theta by sine 2 theta. So d theta is half into sine 2 theta into di by I. Now, in every galvanometer, the most important consideration is the sensitivity of the galvanometer. So sensitivity of the galvanometer, the concept is that there should be a significant value of d theta. For any change in I, there should be a significant change in theta as well. So that means the maximum sensitivity will happen when theta is 45 degree. So in a galvanometer, for efficient galvanometer, we want the sensitivity should be high, and the sensitivity in this formula, you can see it will be highest when theta is 45 degree. Okay, next we come to moving coil galvanometer. See, in a moving coil galvanometer, there is a coil which is wrapped around a soft iron core, and it is suspended with a strip on top and a spring below. So this particular strip is capable of torsion, and the torsion constant of this strip is equal to K. So this strip is capable of torsion and the torsion constant is K. So when you suspend it between the north and south of a magnet, then this is what happens. There is a deflection, because we know that when you suspend a coil in a magnetic field and when current passes through the coil, so there is a torque. So the torque is given by number of turns into current into area of cross section into B. Ultimately, when the torque balances with the restoring force, so the restoring force is torsion constant into theta. So at that time the deflection stays. So when NIAB becomes equal to K theta, so that is a steady deflection. Another thing you will notice that the pole pieces are cylindrical, so you will see that they have a concave appearance. So the pole pieces are concave. The reason is that the field lines will be radial. So for radial field lines, the field lines will always pass through the center of the soft iron core, and you will notice one thing, that the way the turns have been done, these turns are parallel to at least one or more than one field lines, and that is very important because it gives maximum torque. So the radial field lines, they concentrate the magnetic field and therefore they give maximum torque for a given current, because the B is enhanced because of the fact that the field lines are radial. So NIAB becomes equal to K theta. So I becomes K divided by NAB into theta. Now this K divided by NAB is called galvanometer constant, right? So K by NAB is called galvanometer constant. Another thing, theta by I is called sensitivity of the galvanometer. Theta by I is known as the sensitivity of the galvanometer. So suppose we want high sensitivity. So for high sensitivity, K divided by NAB should be high. For high sensitivity, K divided by NAB should be high. NAB divided by K should be high. So NAB divided by K is high. This can be ensured because of the soft iron. So the soft iron ensures that the value of B is high and therefore the sensitivity is also high. Okay, next we come to magnetometer. Magnetometer, like I said, it is used to measure the magnetic moment of a magnet. So again, there are two types of magnetometer. The first one is known as deflection magnetometer. Now this time what we will do is, there is a frame, in which there is a circular scale. In fact, there is a box rather, this thing is a box in which there is a circular scale with a compass needle pivoted like this. Now, with respect to this compass needle, the magnet is placed in a end-on position. So, with respect to compass needle, magnet is placed like this in end-on position. And by the way, this is a wooden scale of significant length. So, we know the distance from the center of the magnet to the center of the compass. Now for end-on position, the formula to find the field is mu naught by 4 pi 2 into capital M into D by D square minus L square whole square. Now the thing is that the horizontal component of the Earth's field will point like this, and you know that the field due to the magnet will point like this, and we can easily measure this angle theta from the circular scale. So you can see that tan theta is coming B by BH. So this means that B is equal to BH tan theta. So we will equate this to BH tan theta, and since all other parameters are known, we mu naught by 4 pi is a constant, we know D. L, of course, the length of the magnet is 2L. So D, BH is known for that particular region of the Earth, and theta from the scale, so we can find the magnetic moment. Now in a deflection magnetometer, when the magnet is placed like this, or rather when the wooden frame is placed like this, means along east-west, then this is called the tan A position. So when the wooden frame is placed along east-west, this is known as the tan A position of the deflection magnetometer. Next we come to tan B position of the deflection magnetometer. So this is the circular scale, and the compass needle has been fitted over here. So I have placed the magnet like this. This is east, west and north, south. Now you will see this time the wooden frame has been placed along north-south, and this time the magnet is in the broadside position with respect to the compass needle. So you know that for broadside the formula is mu naught by 4 pi m by d square plus L square to the power 3 by 2. In the meantime, the Earth's field is like this, and the field due to the magnet is like this. So we can easily measure theta from the circular scale, and you can see that tan theta is B by BH. So we can say that BH tan theta is mu naught by 4 pi m divided by d square plus L square to the power 3 by 2. So once again all the parameters are known to us, and we can easily find out capital M, which is the magnetic moment of this particular bar magnet. So this is deflection magnetometer in the tan B position. Now we come to the second type of magnetometer, which is known as oscillation magnetometer. So this is the second type of magnetometer. What is done is that initially a magnet is suspended in such a way that the north pole of the magnet points towards the north. So initially a magnet is taken and it is suspended in such a way that the north pole of this magnet points towards the north. Now in this scenario, it is given a slight deflection. So it is given a slight deflection. So due to the deflection, let the deflection be theta. So due to the deflection, the force on the north pole of the magnet is m into BH, and the force on the south pole of the magnet is also m into BH. The deflection angle is theta. So due to this deflection, and one more thing, let the length of the magnet be 2L. So due to this deflection, there will be a restoring torque. So restoring torque will be two into m into BH into L sine theta. So you can see that the angle theta is clockwise, but the restoring torque is anti-clockwise. That is why this minus is there. So this will be minus m into BH into sine theta. Now theta is usually very small, so torque will be minus m into BH into theta. Now you know that torque is equal to I alpha. This is the formula. So we can say that alpha is minus mbh by I into theta, And if you compare this with the standard alpha equal to minus omega square theta for any simple harmonic motion, then you will see that omega is coming root over m into bh by I, and therefore time period is 2 pi root over I divided by m into bh. So what happens is that by means of a stopwatch, the time for 20 oscillations is measured. That helps us to find the time period t. I is known because this bar magnet has definite dimensions. BH is known, 2 pi is a constant. So we can find the magnetic moment of this bar magnet. So this completes oscillation magnetometer, and it also completes the second and the final session of this chapter, permanent magnet.